This week we're going to look at Chapter 14. We've been kind of working our way up. We've looked at deformation, we've looked at how it works on a small scale, on a moderately large scale, and now we're going to look at the whole Earth. So whole Earth structure and plate tectonics. Tectonics refers to a physical process that yields regional scale geologic features. So large things, the size of a state, maybe a little bigger, maybe a little smaller, but large scale features. On the largest scale, the Earth is made up of three parts: crust, mantle, and core. This should be something that you're very familiar with already from earlier geology and physical science classes, but we're going to take a closer look at it than you probably have before. We're going to look at how we can use rheology and or seismicity to define layers. We're going to look at what the lithosphere is, what the asthenosphere is, where some other breaks are within the Earth. Now, looking at things seismically. This is a relatively new way to look at the interior of the Earth, and a very accurate way to find out where certain kinds of boundaries are. It works because seismic velocity through different kinds of rocks is different. The vibration waves move at different speeds depending what they're moving through. This is something that we already know from other things like the speed of sound through air versus the speed of sound through a steel railroad track. That's why in the old Western movies you'd see somebody put their ear down to a railroad track to listen for things in the distance, because since the sound waves travel quickly through the dense steel, they could hear things from further away. They would reach them faster than through the air and further than through the air. In the rock, we have velocities that range from 4 kilometers per second to 13 kilometers per second. So it's a pretty big range of velocities, and they're all quite fast. The velocity of these vibrations can change abruptly when it passes from one material into another. When there's an abrupt change, we call it a seismic discontinuity. We know that the material is changing because of the velocity changes. And we can tell that there are velocity changes because there's refraction. Just like light refracts when it's going from one material to another, like the sunlight going through the air, hitting the water and entering the water, there's refraction. When a seismic wave moves from one kind of rock to another kind of rock, there's refraction. This tells us that there's one of two things: a composition change or a phase change. So either it's changing, there's one mineral or mineral assemblage above the discontinuity and a different composition below the discontinuity, like at the core mantle boundary, changing from olivine peridotite material to a nickel iron core. Very distinct composition change. Or it could be a phase change. We've mentioned before that there are certain minerals that as you compress them, they change into another mineral, not because they change composition, but because they rearrange. Once they become rearranged, they're denser, and they transmit seismic waves at a different velocity. Now, there are two kinds of seismic waves that travel through the Earth. There are 4 kinds of seismic waves that you learn about if you take geophysics, but only 2 of them travel through the Earth. The other 2 are surface waves. The 2 kinds that travel through the Earth are called P waves and S waves. Nice, straightforward names, not complicated to remember, and remember which one comes first, because P wave stands for primary waves. S wave stands for secondary waves. So this tells us P waves get there first. They're the primary waves. They're faster, and very importantly, they can go through both solids and liquids. P waves are compressional waves. It's like pushing on the end of a spring. You tap the end of the spring and you can see a wave of compression move down until it gets to the far end of the spring and is released. S waves, the secondary waves, are slower than the P waves, and very importantly, they can only go through solids. They do not go through liquids at all. This is because they're shear waves. You can shear a solid. You cannot shear a liquid. By shear waves, we mean they're the side-to-side and up and down motion. It's kind of like if you've ever held a long rope and you snap it up and down real quick to see that ripple move down the rope. It looks kind of cool. It's a neat little trick. It's an example of a shear wave. Now, this is roughly what we can expect if we have an earthquake over here on the side of the Earth where it says focus. It's the focus or focal point of the earthquake. And as the waves go down into the Earth, because of density and composition changes, they don't travel in straight lines. If there was no density or composition change, it would just be straight lines like you would expect waves moving out from a source. But there is refraction, minor refraction causing curvature when it's just density changes, and then abrupt refraction when there's a composition change. So we can see that the waves are heading out to all different points along the surface of the Earth until we see this one that comes along and hits at 103 degrees, labeled ray A. It's just barely nicking the core. Anything that hits the core, on the other hand, refracts abruptly. And based on the angle that they're hitting this curved surface, they'll refract differently. And it turns out that this ray here that comes out at 143 degrees is the very next seismic wave to reach the surface of the Earth on the other side. We could have 1,000 seismographs set up between that 103 and 143 degrees if the earthquake is right where it says focus, and those seismographs would not pick up the earthquake. Everything less than 103 degrees and everything greater than 143 down to the next shadow zone would pick up the earthquake. This area where nothing is detected is called a P wave shadow zone, and it's because of the refraction through the core. Basically, it's the gap between the last wave that misses the core and the first refracted wave to reach the surface on the other side. There are 2 of these. 2 P wave shadow zones, kind of either side of the core, located about like that. And they're 103 to 143 degrees from the focus point. Now notice this isn't 103 and 143 from north, because they're both labeled 103 and 143. So it's 103 degrees from where the earthquake happened to 103 to 143 from where the earthquake happened in both directions. Those are the P wave shadow zones. Not as important to remember exactly how many degrees, more important to remember the approximate locations and what they are. For S waves, we have a huge shadow zone because they don't refract through the core, they actually just stop. The outer core is liquid. This is actually how we know that the outer core is liquid. We have this massive shadow zone. Extends all the way from 103 to 103 degrees. Basically, still the last wave to just barely miss the core on either side, and anything that hits the core, if it's an S wave, simply stops. So there's a massive shadow zone. When we look at a wave going down through the Earth, each time it goes through a change in composition, like crust to upper mantle, lower mantle, outer core, inner core, there's a little bit of refraction. You notice that within the mantle, for example, it's slightly curved. As soon as it hits the outer core, there's an angle. It changes direction slightly. Then it comes down, hits the inner core, bounces off, comes up. Some bounces off, some actually gets refracted through and goes to the other side. There's both reflection and refraction happening every time it hits one of these boundaries. If you want to learn more about that, understanding why and how much and how to understand the results of these different seismographs around the world, geophysics is the class that you want to look at. We're just looking at what we can learn on a large scale from this. We're not going to look at like what the oil companies are doing and stuff like that. That's geophysics. So we have a source over here, an earthquake, a nuclear weapon detonation, something huge. The seismic waves travel all the way down to the center of the Earth, bounce back, and come up at this seismograph. Seismographs anywhere along the way are going to have waves hitting them unless they're in that shadow. But, it might be waves that bounce off the first interface, second interface, third interface, bounce a few times. Lots and lots of bouncing and refracting going on. So, seismically defined layers. We have a crust, an upper mantle, a transition zone, a lower mantle, an outer core, and an inner core. So these are the key large changes in seismic velocity. There are also several small velocity changes, some of which are in the transition zone and some of which are elsewhere. You can see here a profile as we go down through the Earth. We have this left-hand side is showing S waves. They're to the left because our velocity is across the top here. And S waves are slower. They're the secondary waves. Our P waves are further to the right because they're higher velocity. They're the primary waves that get there first. So we're coming along, and this dashed line is the base of the crust. And you can see that as soon as we get into the very top of the mantle, things start slowing down a little bit. They slow down because the top of the mantle, the material changes from being very rigid and brittle to being more plastic. That's how we're saying that we're changing from crust to mantle, plus composition change. And as we get deeper and deeper, it gets slower and slower as it gets hotter and more mushy, but then it starts increasing in velocity because of the pressure and because of phase changes. And so we have more velocity changes, and we hit this transition zone, and then below that transition zone is the lower mantle. Within the lower mantle, it's fairly consistent. The composition isn't changing, it's just an increasing pressure, and so we have this very slow increase in velocity until we hit the outer core. Then our S waves drop to zero because they're gone. S waves cannot go through that outer core. Our P waves over here to the right, on the other hand, increase in velocity very rapidly as we get deeper into the crust, and then they slow down and they change a bunch of times until we hit the lower mantle, and then again fairly consistent increase until we hit that outer core boundary. For the P waves, they don't stop though. They slow down dramatically from about 13 kilometers a second. They slow down to about 7 kilometers a second because, they're hitting a different material and it's liquid. But as you go down through the outer core, the pressure is increasing, and so the velocity is increasing because the density is increasing. We hit the inner core, which is solid, and there are some new S waves. They didn't magically appear. Again, this is explained in depth in geophysics, but all the vibrations going on, even from the P waves, can generate new S waves. So these S waves in the inner core were created by that P wave that traveled through the outer core. Of course, it gets to the other side of the inner core, and it can't push its way out through that outer core, and so that S wave stops again. P wave goes through and makes it all the way out to the other side of the Earth to where some seismograph picks it up. But you can see this pattern of as you go through any given layer, the velocity is increasing, and then when you change into a new layer, there's an abrupt change. Could be 1 kilometer a second, half kilometer a second, 6 kilometers a second. No matter how big or small it is, it's an abrupt change. On the other hand, rheologically defined. So this is not about seismic velocity. This is about what is it? How does the material behave? Because you remember, rheology is the ability of a material to flow. So we have a crust. We're all familiar with a crust. We have the upper mantle and the lower mantle. We still see a transition zone. This is, in this case, transitioning material. Just so happens that the seismic transition zone is in the same place. It's transitioning because the material is changing, which we see here. We have the lower mantle, the outer core, and the inner core. Something that I think is interesting, because a lot of times people think of the core as really small. You notice how thick the mantle is? 2,885 kilometers. The outer core is almost as thick, 2,255 kilometers. And then the inner core, this is just to the center, so this is the radius of the inner core, 1,200 kilometers. So the core as a whole is actually thicker than the mantle. That's just something to keep in mind if you're sketching the Earth. So up here, if we zoom in on the top of the Earth, we see the crust, and then we see something labeled lithospheric mantle. So it's part of the mantle, but it's not even all of the upper mantle. So you notice within that box, this gray area doesn't extend to the bottom of the upper mantle. And below it we have asthenospheric mantle. So the upper mantle is split between two parts, so it's subdivided even further. So as a comparison, we can see the crust right up here at the top, and we can see the crust right up here at the top. We can see the upper mantle with a transition zone, We don't see this low velocity zone showing up in the rheology defined layers though. There's no extra layer in that upper mantle. Then we have our our lower mantle and our lower mantle. Same boundary. That transition zone is 400 to 670 kilometers down. Over here it's 400 to 670 kilometers down. Then our outer core starts at 2,900 kilometers down. Same for the rheological. And then the inner core at 5,155 kilometers down, and same thing for the seismic. So for the inner layers of the Earth, they agree very, very much. The seismic discontinuities are caused by those composition changes that we see in the rheological model. It's just up in the upper mantle that we see a real difference.